Okay, let's go ahead and get started. A lot to get through today. This example that helps you for your next homework assignment. Our question of the day last time had to do with playing sports. So there's the answers to that. Actually, I was a little surprised at how many people had said no, but at any event, that was kind of the question of the day. I want to begin by showing you the execution of your next programming assignment. So I'm going to go ahead and run this. You have reached a point now where you're able to write a Hangman program. How exciting. Guessing game, where you're trying to guess the letters of a word. How about if we use 5-letter words? It's too bad because, it's fun to have an audience to be able to have you make the guesses, because otherwise you might think that I'm kind of not making very good guesses. But, the idea is it's picked a 5-letter word for us to guess. And then when you play Hangman, you kind of draw a picture of a head and then a body and then like legs and arms. So how many guesses do you get? It kind of depends upon how many of those body parts you end up drawing for the Hangman. 7 guesses is typical, but I'm going to go ahead. I'm going to give you 12 guesses for this program. So let's see. 5-letter word, we don't know what it is. What are we going to guess? E is a pretty common letter. Let's see if there's any E's. There are no E's. How about any O's? There are no O's. How about an A? No A's. How about an I? So I've done A, E, I, O, and none of them are in there. How about a U? There is a U, so it would be surprising if there were, if it didn't have any of these vowels. S is pretty common. T, there was an S, that's good. T is pretty common, but no T's. How about P? Is pretty common. An R, an M. I'm starting to run out of guesses. No M's. How about a B? There are no B's. We're down to just 3 guesses. How about a G? There are no G's. How about H? There are no H's. How about N? There are no N's. The answer was cuffs, and we lost the program. We lost the game. I don't know if you had a sense of this, but this is a slightly different kind of Hangman. I'm going to change a setting in the main program so that it shows me something that I didn't have it showing before. Let me explain to you what's going on. Let's go ahead and hit run. So how about if we do 7-letter words this time? We'll give ourselves 12 wrong answers again. What it's telling me is that it knows of 21,729 7-letter words. And we call this evil Hangman. This is a cheating Hangman program. It's kind of like it wants to win. So if it wants to win, it has not yet chosen the word that you're supposed to guess. It's kind of keeping its options open, and it has 21,729 of those options. So if you guess an A, it says there's no A's, and now it's down to 11,580 words, but it still has a lot of options. E, no E's. I, there is an I. It's down to 898 options. How about, see if there's any other O. How about a U? There was a U in there. Now it's down to 294 options. S, T, you can see it's the number of options, number of words it knows about that fit that pattern is going down steadily. M, there are no M's. How about a B? There are no B's. It's down to 78 words that it knows about. How about an R? There are no R's. How about P? There are no P's. It's down to just 43 words, but we're down to 3 guesses. So how about an N? There is one N, so we got some. How about a G? And there was a G, so it ends in ING. We're on a roll. Maybe we can win this after all, but we only have the 3 guesses left. How about a C? No C's. How about D? There are no D's. We're down to 1 guess left, and it knows of 8 words that fit this pattern. So how about an L? There are no L's. The answer was fuzzing. It never got to the point where it was actually playing Hangman. It never picked a single word. It was kind of still cheating at the end. It had 8 possibilities. So it's an interesting game. It's kind of a fun game. You can a lot of students tell me that they have their friends play it to kind of humble them, to show them that they're not very good at playing Hangman. When you're done, you could do something like that. All right, so today's lecture is meant to prepare you for working on this programming assignment. I'm going to begin by talking about some string processing, because this program does involve string processing. We did that in 142, but I've seen some students struggle with this. So I don't want that to be the part of the program that's hard. So I'm going to write a little method with you called dashes, where if you give it something like the string hello, what I want it to do is I want it to take a string like hello, and I want it to return a string that has dashes in it, H-E-L-L-O. You're going to do similar things in the homework assignment. So public static, it's returning a string. It's called dashes. It takes a string as a parameter. What's it going to do? It's going to make some string that we could call result. We don't know what to start it as, that it'll return at the end. In between, it's going to process this string. So there's a standard traversal loop for a string. For int I starting at 0, I less than s dot length with parens, I plus plus, and inside of here, do something with s dot char at I. So we'll kind of remember that that's how we do string processing. What we want to do here is something that's the string equivalent of a cumulative sum. We'd like to build up a result. So we could say something like our result should be the old result. How about plus a dash plus s dot char at I? So how about if we kind of do that? What do we initialize it to? What's the string equivalent of starting at something like a 0? It would be an empty string. So we make an empty string, we add various characters with a dash, so we can go ahead and compile and run that version. And we get hello with a dash in front. Oh, so I shouldn't have put the dash here. I should have put the dash after the s.char. I think you know that's not going to work either. What kind of a problem is this? From 142, this is a fence post problem. We have 1, 2, 3, 4, 5 characters in the word, but we want only 4 dashes because the dashes separate, but we don't have dashes at the beginning or at the end. Classic fence post problem. So the fence post solution to this would be to do the first character outside the loop, s.char at 0. We could kind of do that here, and then to start this at 1. So we do the very first one outside the loop, and then we do dash char, dash char, dash char. So character at the beginning, and then the loop does dash char, dash char, dash char. If we try compiling that version of it, Java's not very happy with s.char at 0 because that's a character, and it wants a string. So how do we turn something into a string? When I first was teaching Java, I remember I was using a textbook from a fellow named Kai Horstman. Kai's a friend of mine. And I remember asking Kai kind of, what do you advise in a situation like this? Because there's lots of library methods that will do things like converting things into strings. And Kai said, no. You say quote, quote, plus. And I said, isn't that a little weird? And don't novices find that confusing? And Kai said, too bad. This is how it's said in Java. If you want to be a Java speaker, you will use Java idioms, and quote, quote, plus is a Java idiom. It's actually a nice idiom in that everything can be converted into a string. Absolutely anything can be converted into a string in Java by saying quote, quote, plus. So that concatenates an empty string with that character. So we could kind of compile and run this version of it. And now we've got our hello with dashes in between. I normally ask, are there any cases that we might need to worry about? And I usually get someone who points out that this isn't going to work if the string is empty, because it assumes there is a char at 0. We could fix that up with an if-else or something, but I kind of like the idea of just having a precondition that says s is not empty. This is not a method that deals with empty strings. That could be quite reasonable. If you're playing Hangman, for example, you don't play Hangman against an empty word. So there's sometimes when it's reasonable to just kind of assume that something is not empty. But that's kind of a precondition we would have wanted to record about that particular method. So this is meant to be a helpful hint. It'll be in the notes for today so that you'll be able to review that if you need to remind yourself about individual character processing. All right, the next thing that I want to do is to go back to this Friends program that we were talking about. And we were working on the code that would read in the input file, and it would build up a structure that would record all of these different friendship relationships. So for all of these different people, it would kind of build up a structure, and we were trying to get to a point where we had a map that had this kind of information in it. For each person, we could look up, say, Ashley, and we could find a set of her friends. That was kind of the goal of what we were doing. There was some code that was reading in lines, looking for the lines that had dash dash in it. That's from the input file. And then it pulled it apart into a name 1 and a name 2. And it added friends in both directions because friendships go both ways. And so this was the method that we were working on last time. And I'm going to spend a fair amount of time here going over this method very slowly and carefully, because it's really important for you to understand this method. It is a medium hint for the homework assignment. So I highly recommend that you get to the point where you understand what's going on here before you try working on the homework assignment. And I'm going to show you something at the very end that kind of relates this to your homework assignment, so you'll see how it's relevant. But so what we did is we had an if-else. I had mentioned that it's common with maps that you have different code that you execute for the first time that you encounter some potential key versus later times when you've already seen that key before. So that's why we're using contains key. So when we entered, I think with Ashley Christopher as the first pair of names, we'd never seen Ashley's name before. It wasn't in the map. So we needed to construct a set of Ashley's friends, and then we needed to tell the map to associate Ashley's name with that set of friends, and we needed to add Christopher's name to her set of friends. So we executed those 3 lines of code. Then we came back around and we did it in the other order, where Christopher's name was first and then it was Ashley. And the map didn't have an entry for Christopher, so we executed these 3 lines of code again. We made a set, a brand new set that was going to record Christopher's friends. We told the map to associate Christopher's name with that set, and then we added Ashley's name to that set. I was using this little file here where I was kind of building up a list here of, we started with a map, and then the first time we did an add to, we ended up adding an entry to the map for Ashley that would store a set of friends for her. The next time we called add to, it was in the other order, and we made a set for Christopher's friends and told the map to kind of associate that with Christopher's name. Every time we execute these 3 lines of code, every time we execute these 3, we end up adding a new object. So that would be building up this list. I'm not going to bother to keep going with that today, but because I think you kind of get the idea. But I had mentioned that by the time we're done, all 21 names that are mentioned are going to lead to having a set for each of those 21 people. 22 objects total. Our map that's keeping track of everything, and then the 21 sets that we build up. So when you execute the 3 lines of code, you're making a new object, a new set. But I had mentioned, and we were kind of just getting to this at the end last time, that if you encounter Ashley's name again, and we will because Ashley has more than one friend, we're not going to want to make a brand new set because then we would lose track of the old set. So we don't want to execute these 3 lines of code when we encounter Ashley as name 1 the second time. We'd want to do these 2 lines of code where we don't make a new set. Instead, we ask the map how to get in touch with the old set, the one that we've already constructed, and then we add that person's name to that set. So what I would like to do, and it's nicer to do this with people in the room, but you can kind of play along at home and do this along with me. I want to look at several of these different calls that are being made. So I've put a stop here on the println. This is the first call to add to. The first call to add to had Ashley as name 1 and Christopher as name 2. And so I want you to tell me, did it execute the 3 lines of code, or did it execute the 2 lines of code? So 3 or 2, that's kind of the answer. Which or which? Which was it? And the answer here is 3. It was the first time it was encountering Ashley's name, so it constructed a set to store Ashley's friends. And if I let the println command execute, you can see there's that set that it had constructed. Before the call on the method, the map was empty. Now the map has an entry for Ashley with a set that has 1 name in it, which is Christopher's name. Okay, let me scooch this a little more. Oh, there it was. There is a little command here that's going to let me kind of just run again until it hits a stop. So it kind of went back and it made the next call on add to. The second call on add to had Christopher followed by Ashley. So is it the 3 lines of code or the 2 lines of code? It's the 3, because this is the first time we've encountered Christopher as name 1. So it needs to create a new set, add a new entry to the map, and put Ashley's name into that set. And that's what we see when we do the println. There is a new set here that's associated with Christopher's name. So now there's 2 entries in the map, that's keeping track of 2 entries that point at 2 different sets, a set to store Ashley's friends, a set to store Christopher's friends. Well, then what happens when we let it run again? It goes to the next line of input, and the next line of input had Ashley's name first and Emily's name second. So is it going to do the 3 lines of code or the 2? The 2, because it's already seen Ashley's name as a name 1. It already has an entry in the map for Ashley. That entry has Christopher's name in it. We don't want to lose that set because we'd lose track of the fact that Christopher's a friend of Ashley's. What we want to do instead is execute the 2 lines of code, so we don't make a new object. We instead just put Emily's name in this existing set. So that's what we're going to see when we let that line of code execute, is that Emily's name has been added to the set, but we didn't make a new set. We executed the 2 lines of code. Let's let it run again, and we have Emily Ashley, because it's doing it in the other order. So does it do the 3 lines of code, or does it do the 2 lines of code? The answer is it does the 3 lines of code. This is the first time we've seen Emily's name as a name 1. There is no entry in the map for Emily's name. We didn't have a set to store her friends until this call here. But so we would have executed the 3 lines of code. I would have added a line here, to say that we had Emily's friends, our new object we're keeping track of. And it puts Ashley's name into that set. So that when I go ahead and let it execute, there's that 3rd entry in the map. Emily's name is associated with a set that has Ashley in it. All right, maybe we'll do just kind of one more to see. So we let it run again, and now we have Ashley Joshua. So does it do the 3 lines of code, or does it do the 2 lines of code? It does the 2 lines of code, because it already knows about Ashley in the map. It's already made a set to keep track of her friends. It's already put 2 names into that set. This is a 3rd friend of Ashley that we're encountering, so it executes the 2 lines of code to add Joshua's name to these 2. So it adds Joshua to the existing set. And I didn't quite hit the button. I wanted to Ashley Joshua. I think I wanted to let it run. I think I didn't let it go. Okay, and then we'll let it execute. And where is our println? Oh, I think actually it did do the println, but I've kind of gone beyond. Sorry. But here was that 3rd friend, and I hadn't scrolled down, so that's why I wasn't seeing that there was actually a line of output there. So that was the adding the Joshua. Now we're actually on yet the next one after that, Joshua Ashley, which, by the way, does the 3 lines of code, because that's the first time we've encountered Joshua's name. And so we would add it to our map by creating a new set that's going to keep track of Joshua's friends. So again, a distinction between when you first encounter a potential key versus later when it's already in your map. We construct a brand new set the first time, but we don't want to construct a new one later. We want to add to the existing set. So that's very important to understand. Let me go ahead and end this. I want to do one other thing with this. I wanted to mention that this code is a little bit on the verbose side. Most programmers would want to write this in a more concise way. And I'm going to show you that more concise way. It kind of gives you another way of understanding this code. And I've said it's very important to understand this code, so it's good to have another way of looking at it. So let me get rid of the println. So one of the things a programmer would say is, look, why do you have this variable called the friends? You know, you set it to friends.get of name1. So I'm going to copy that. Oops, I didn't want all of that. I wanted friends.get of name1. So let me make a copy of that. And then it used that variable here, but it used it once and only once. So why not just kind of put that there, friends.get of name1, instead of using the variable? So why not reduce it to one line of code? Now we can do something similar here. It's not quite as simple because we do use the friends variable more than once. But so suppose that I made a copy of what I was setting the friends variable to be. And so here, instead of using the variable, I use that thing that I set it to, the new tree set, you know, and then I got rid of this line of code. Well, the thing is, I'm using the friends here. But remember, you know, I was kind of doing this last time when I was adding things here, is I'd initially have it say the friends, but then once I had told the map about this friendship, I changed it to friends.get of whatever the person is. So we don't need to use the variable the friends to keep track, to get a reference to the set that we've made for this person. We can do what we did down here. We can ask the friends map to get us the entry for that name. So I can put that here in place of the variable. I ask the map, tell me what you know, the set that's associated with name 1, and then I add a name 2 to that set. So I don't really need that variable called the friends. Once you get it to simplify to this level, then there's another thing that you could notice. You know, if you remember your 142, we talked about the idea of factoring if-else statements. So this is the last thing in the one branch. This is the last thing in the other branch. Because it's the last thing in both of those branches, it doesn't need to be in the branching. It can just be something that happens after the if-else. So instead of having, you know, a duplicate version of that line of code, we pull it out. So that basically, you know, we know that this is a line of code we want to execute only if that test evaluates to true, but we always want to execute this line of code. And maybe a way of describing it, you know, is we're checking to see whether this is the first time that we've encountered this key. Is this the first time I've seen Ashley's name, for example? If so, I need to make a new set for Ashley, and I need to tell the map about that association. So if it's not in the map currently, I need to put something in the map, and I need to construct the set that's going to hold that person's friends. And I always want to add the name 2 to that set for that particular person. So that second step you always do. But the first step is the first time you're introducing it to the map, and that's the first time you're setting up that brand new set. So I don't have a strong preference. You know, when I've tried to explain the shorter version of the code, I can just tell that people don't understand it as well as they understand the longer version. So if the longer version is easier for you to understand, that's fine. But I did want to let you know that this is kind of how most programmers would tend to write it. Let me make sure it still compiles properly. If I had left in the println, what you would find is that by the time it's done, it has constructed exactly this thing that I said we were interested in. A map with 21 entries where each name is mapping to a set that has that person's friends. Okay, well, I want to spend a little time going over this friends program. Let me come back over here. Let's go ahead and let me show you a sample execution of the friends program. How about this time I'll start with Jessica, and I'll see kind of what's the connection from Jessica to Stuart. So this was kind of the problem that we're solving. Remember that we had this friendship map here that we're starting at Jessica and we're trying to figure out how to get from Jessica to Stuart. And so what it ends up doing, so the way that I kind of like to think about this is that when we run this program, we begin by saying, who it is that we're starting with, and that becomes the center of our universe as we solve this problem. So we're starting with Jessica. So, you know, in looking in our map here, drawing, you know, we would start with Jessica, and then what we're doing is we're kind of finding concentric circles, friendship circles. So from Jessica, we find the ring of friends who are one away. That's Michael and Ashley. So that's kind of, you know, that's the one away folks. And, you know, notice that's what we print first, is Ashley and Michael. And then what do we go in going from one away to two away? What we do is we take the current ring, the friends who are one away, and we make kind of an outer ring, which are the friends of those friends, friends of friends. So I would find Michael's friends and I would find Ashley's friends, and that lets me now have a ring that's one further out than it was before, the friends who are two away. And that kind of gets me to where I am here, Christopher, Emily, and Joshua. I still haven't found Stuart, so I extend the ring one more. I find their friends. And so now I have friends who are three away from Jessica, and I still don't find Stuart there, so I look at friends who are four away, and that's when I encounter the name. So this is a complicated task. This is a non-trivial program. And I don't have enough time to cover it all extremely carefully, you know, because I spent the time on that other part that was more important for you to understand. But don't worry about it. This other part is less relevant to the homework, so, you know, it's not so important that you understand it. I mean, I like the option of having a somewhat more complicated problem to work on. So I like looking at something that's a little more than what I'm going to ask you to do, say, on the homework. But so let me come back to my main here. I had commented out some lines of code that I'm going to put back in. That I just kind of wrote some simple code so that we didn't have to write it together. It makes a scanner. It asks for a starting name. How are we going to know whether a person is known or not? That's whether or not they're in the map. So this is going to involve doing a call on friends.contains key name one. And we want to know if the map doesn't know about that person. So that's another case where we'd use that negation. So if it's not in the map, we'd say we don't know about that person. We can't find him. And otherwise, it's going to show, it's going to ask for a target. You know, in this case, the target was Stuart. And then it calls a method called show matches. So this is what the show matches is, kind of this other method that we're going to write. We'll get a good start on it, but we're not going to have time to write the whole thing. Public static void show matches that takes our map. Remember, our map takes the name of a person, a string, and it maps it to a set of string, a set of their friends. And we're calling our map friends. And as with the other methods here, we have a name one and a name two. In this case, we're trying to kind of find what's the connection between these two names. And if you look at what's going on here, you can kind of see it's doing one away, two away, three away. There's some kind of a loop that's going on here that's keeping track of a distance, how far away. So how about if we said that we were going to start with things that were one away, and I'm going to say, while we haven't found name two, what are we going to do? We're going to do a distance plus plus. So remember what I said is, if we didn't find Stuart in the ring that was one away, we're going to kind of compute the ring that's two away. So we're going to go from being one away to being two away. And if we don't find it there, we go to being three away. If we don't find it there, we go to being four away. So we're going to increment our distance and then do an update. And so that way at the end, we're going to be able to say something like system.out.println found at a distance of distance. You know, that's little output here, found at a distance of such and such. So how do we do the update? Well, this is a problem, I think, where, I think we've probably got you a little bit nervous about setting up extra data structures. It's good to have some nervousness. We don't want you to use extra data structures that you don't need. And you can lose style points if you introduce data structures that you didn't really need. So we want you to be efficient in that sense. But this is a case where we really do want extra data structures to solve a problem. What I'm going to say here is that there's going to be some set of strings that I'm going to call current group. Because, this idea of I'm going to find kind of who's one away, the ring of friends were one away, and then two away and three away, I'm going to call that current group. And I'm going to keep that as a set. So I'll make that a new tree set. Set of string, is this new tree set. And so how do I set this up initially? Well, initially, I want this to be keeping track of Ashley and Michael, the friends who are one away. Where do we get that? Well, that was exactly what we were trying to do with our map, is that the map knows that Jessica is associated with the set that has Ashley and Michael. We know who her friends are. That, this first one is really easy because it's in the map. Now, you might imagine that what we would do is point at that set that's in the map. But we don't want to do that because we're going to be doing a lot of manipulations with this thing called current group, and we don't want to damage what's in the map. We want to kind of preserve what's in the map. So what I want to do is, the map, and so how do we get at that set that's in the map? Friends.get of name 1. So when name 1 is Jessica, friends.get of name 1 is going to be a reference to the set that has Ashley Michael. That's a set. What do I want to do with that set? I want to have all the things that are in that set added to this set called current group. So how do I do that? We did a little bit of practice with sets, not all that much, but you may remember that there was a method called add all. So I can add all of the entries from one set into this other set. So I'm gonna kind of add Ashley and Michael's name because it's over here. The map is keeping track of that set. And I'm saying take those names that are in that set and put them in my set that's called current group. So, and then how am I going to know whether I found the name? I'm trying to get to the point, current group is kind of my current ring. The friends 1 away, the friends 2 away, the friends 3 away, the friends 4 away. What ends up happening that tells me that I'm done? Well, when I end up here where I've got the friends, that are 4 away, I know I'm done because Stuart's name is in there. The name I'm looking for is in there. So what we can do here is we can ask whether the current group .contains. Sets have a method called contains name 2. We're looking for the connection to the name 2. So we're looking for a point where my name appears in a ring, because then I found the right ring. I've kind of found the thing however far away. Now, that's when we would stop when it finds the contains. But remember, the while loop tests why we would continue. So we want the negation of that. While we haven't found that name, that means that whatever the current ring is, it doesn't have my name in it. So we need to move one out. So how are we going to do that? How are we going to move one out? Well, we're trying to replace kind of say the friends who are 1 away with a ring that has the friends that are 2 away. So we're kind of trying to make a new set, a different set, that's got the friends of those friends. So I'm going to introduce a brand new set for doing that. I'm going to have a set of string that I'm going to call next group, which is a new tree set. And how am I going to set that up? This is maybe this little bit of code we're about to write is in some sense the most interesting little bit of code. It's kind of the core code that we're writing. We're trying to deal with friends of friends of friends of friends of friends. So what do we want to do? So suppose that we've got to the point where we've got Ashley and Michael in our current group. How are we going to find these folks who are supposed to be in the next group? Well, if we were here, we would say, well, if we were looking at Ashley, we want to add Christopher, we want to add Emily, we want to add Joshua, we want to add the friends of this friend. So for all of the different things that are in the current group, we want to add their friends to the new group. So, okay, let me back up a little bit. For all of the people who are in the current group, what does that sound like? How do we get all the people who are in the current group? There's a set that keeps track of all the people in the current group. We can use a for each loop. So, and the current group is a set of strings, so we know this is going to be a string. I could say for string S in, but here we can use a kind of more specific name. That's the name of a friend, or a friend, or a triple friend, or a four-way friend, but I'm going to use the name friend. So for all of the friends that are in the current group, what is it that I want to do? Well, so that would be, for example, the first time through, that's going to be Ashley. I'm interested in knowing friends.get of that friend. Who are Ashley's friends? And the map, remember, will tell us that. The map knows how to refer to this set of Ashley's friends. What do we want to do with Ashley's friends? We want to add them to what's going to be the new ring. So I want to say next group dot add all the friends of Ashley. So kind of the first time through this for each loop, friend would be set to Ashley, and we would add all of her friends to the next group. Then we'd come around the for loop, and then the friend would be set to Michael, and we would add all of Michael's friends to this group. So it would do two things. It would add in the two groups of friends, the friends of Ashley and the friends of Michael. So current group has got friends of friends. It's kind of extended our ring out by one. And then that becomes our new ring. So instead of looking at friends one away, we're now looking at friends two away. So we would want to reset our current group to be that next group, is that next group. And then I could say something like system.out.println. I could produce a line of code that looks like one of these lines of code. It begins with some spaces to have a little indentation. 1, 2, 3, 4 spaces. And then it's got a distance, and then it's got the word away with a colon. And then it's got that next group that kind of shows who's in that next group. So that's kind of, we produce a line of code sort of like that. Let me compile and see what it produces as output when we do that Jessica and Stuart. Well, it is finding me 4 away, but it's got a whole lot of extra stuff in there that we didn't see before. It's also not showing friends who are 1 away. It's saying that Jessica is 2 away from Jessica. That's kind of a funny idea. Let me show you actually an interesting thing. What if I run this and I say, starting at Jessica, tell me how far away Jessica is. And what it does is it says that Jessica is 2 away from Jessica. Is that the right answer? Is Jessica 2 away from Jessica? I don't think so. I think Jessica is 0 away from Jessica. You're already there, if it's the same person. So I think I steered you badly initially. We don't want to start at a distance of 1. Let's start at a distance of 0. So we'll kind of throw in a special case where, and we'll make a current group. But now current group is much simpler than it was before. Current group is just whoever is name 1. So, what we're going to do is if Jessica's the center of our universe, we start with Jessica herself, just Jessica's name, and being 0 away. So we kind of start at a distance of 0 with just Jessica's name. So if I compile and run that version, and I say, how far away is Jessica from Jessica, now it's saying 0 away, which is good. It didn't have to do any friends of friends of friends of friends. I mean, actually, if Jessica didn't have any friends, it would say she's unconnected to herself, which would be a little strange. Now, if I say Jessica and Stuart, then I get a lot of lines of code, a lot of lines of output. This first one is just what it was before. Ashley and Michael are 1 away. And then it says quite a few things that are 2 away, and even more things that are 3 away, and even more things that are 4 away. What I would say is that the mistake this code is making right now is that it's allowing somebody to be listed as being, that Jessica herself is 0 away, and Jessica is 2 away, and Jessica's 4 away. I don't think that, any given person is a certain distance away and not other distances away. So we're getting duplicates here. So we'd want to have some way of eliminating duplicates. So we need yet another string that I'm going to call a set that I'm going to call already seen, which is a new tree set. And so inside of our loop, just before we do the updating here, what I'm going to do is I'm going to say already seen. I'm going to add all of the things from the current group. So I'm going to kind of know that I've accounted for things that are in the current group. And then I make a next group here, but before I reassign, I'm going to say next group dot remove all of the already seen. So as we examine these different rings, I'm going to add the names from that ring into the already seen. And then before I do the kind of switch to the next group, I'm going to remove the ones that are the duplicate ones. And if we compile and run and I do Jessica and Stuart, now I'm getting the output that I wanted. This code still isn't quite done. There's one little case we didn't deal with. I don't know if any of you are thinking about it, but this doesn't always succeed. Like if I run this and I say start with Stuart and go to Bart, it goes into an infinite loop. So it may not succeed. We have the wrong while loop test here because we're assuming we're going to find name 2, and we may not. So there's some extra code you have to build in for that, where it's not found at all. So that's in the notes. It'll be in the code that I post for the calendar today. But I think that's enough of discussing this. But so anyway, if you're interested, you can read the notes about that little part of it, that little modification. Otherwise, we've written almost everything. So I want to do this one more thing for you, which is to talk about the homework assignment and to relate what we were doing before, the 3 lines of code and the 2 lines of code. I want to relate it to what you're going to be doing in your homework. And so if we look here, there's under the different resources, there's something here that's labeled a helpful diagram. And if it is a helpful diagram, then maybe we should take a look at it. It's using a very small dictionary of words, and I encourage you to do the same thing when you're testing your program. I have a little file here that we can use that keeps track of this. So this is that small dictionary of words. They're 4-letter words. So initially what we would tell the person playing the game is that the current pattern is dash, 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 dash. You haven't guessed anything correctly. You haven't guessed anything. So anyway, that would be kind of the initial thing. Then what ends up happening is in that little useful diagram, it says that the user guesses an E. Now, what I want you guys to do, the assignment write-up is very clear about this. I'm just trying to give you a little more understanding of it. I'm just kind of trying to point it out. You're going to have a map. And so what you're going to do with the map is the following. There's going to be a current set of words. So this is my current set of words. And you think to yourself, well, suppose that, so the pattern was dash, 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 dash. Suppose that they guessed an E and the answer was actually ally. Then what would you say? What is the new pattern that you would set up? Well, there's no E's in ally, so you would say there's no E's and the pattern is still dash, 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 dash. Okay? This is all built on the patterns, the different patterns. And so does this map have an entry for dash, 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 dash? No, it doesn't have an entry for anything. So we want to have an entry for dash, 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 dash. In what I was saying before, as I said, does it execute the 3 lines of code or the 2? It's executing the 3 lines of code. This is like seeing Ashley for the first time. So we're going to set up an entry in our map that for dash, 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 and it's going to associate it with a set that has that word in it, ally. So it's almost as, ally is a little bit like Christopher. That we're creating a set of words that match that pattern. All right, let's look at the next word, beta. What would the pattern be if the answer were beta and they had guessed an E? Well, the pattern for that would be dash E dash dash. Do you see dash E dash dash in here? I don't. So we'd execute the 3 lines of code, dash E dash dash. We add a new entry that's associated with a set, and we add the word beta to that set. That's what the 3 lines of code do. How about the word cool? what would be the pattern that you would show the player if the word was cool and they guessed E? The pattern would be dash, 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 dash. Do we have dash, 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 dash? We do. It's already in the map. We execute the 2 lines of code, not the 3 lines of code, because it's already there. And we add the word cool to this existing map. We don't overwrite the map. We use the existing map and add the word cool to it. How about deal? Deal, if that was the word and they guessed an E, then the pattern would become dash E dash dash. Do we have dash E dash dash? We do. So that means we execute the 2 lines of code. We're going to add this to the existing set. We're going to put the word deal in there. How about this? Else. Well, that's E dash dash E. Do you see E dash dash E in here? I don't. So it's got to execute the 3 lines of code. E dash dash E. It adds a new entry to the map that has a new set that we construct, and it puts the word else in there. How about flu? That would be dash dash E dash. Do you see dash dash E dash? I don't. So it makes dash, oops, I can do this, dash dash E dash. It executes the 3 lines of code, and it puts the word flu into that set. Good. That would be dash 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 because there's no E's. That's already in the map, so we execute the 2 lines of code and we add it to the existing set. Hope ends in its dash 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 E. Do you see that here? I don't. So it executes the 3 lines of code, adds something new to the map, dash 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 E, adds a new entry to the map that has a set that has the word hope in it. And how about ibex? That's dash dash E dash. Dash dash E dash, that's in there. So we execute the 2 lines of code and we add ibex to the existing 2 lines of code. That's how we process this sequence of words. And then the Hangman strategy is very, very simple. We look at all these different sets and we pick the one that has the most words. The one that has the most words is this one. So that's what we end up doing is we decide that on the next round, we're going to say there were no E's, that the pattern is dash, 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 dash still, and this is now our current set of words. Now let me see if I can relate this to what was here, kind of what's being shown here. So let me scooch this up a little bit. And I think you can see that I'm showing you the same thing that the diagram is showing you. That it goes through these various words and it splits the words into different sets that our map is going to keep track of based on the pattern. So there's that dash, 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 dash pattern that has the 3 words. There's the dash E dash dash that has beta and deal and so forth. So it's showing you the different patterns. It's the exact same thing that I've shown you right here. And it continues. It kind of shows, okay, well then we'd pick ally, cool, and good as our next set of 3 words. And what would we do then? Then we say the pattern is dash, 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 dash. And then if the user here is guessing an O, we do the same kind of thing, and we have a set that has 2 things in it and a set that has 1 thing in it. We pick the set that has more things in it. So that useful diagram is going to be useful to help you to understand the what's going on here. And I hope you understand then this relationship between the code we were looking at before, the 3 lines versus the 2 lines, because you're going to be doing the exact same thing. That's why it's a medium hint for your homework assignment. You're going to be doing the exact same kind of thing to process the list of current words. Let me also just kind of say one thing. Some people seem to get the idea that they need to think of the possible patterns or generate possible patterns. You don't need to generate the patterns. It's the words themselves that generate the patterns. The reason that we have a dash, 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 dash pattern here is because we came across the word ally, and we realized that it would have the pattern dash, 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 dash. And so we added that to our map because there was a word that would have that pattern if we were actually playing Hangman. Similarly, when we saw the word beta, we saw that that would lead to the pattern dash E dash dash, and that's why there's an entry in our map for that, because we encountered a word that would have had that pattern if we were actually playing the Hangman game. Okay, that's what I wanted to go over for today. We'll do more in Monday's lecture.